Hey guys, and welcome back to another video on the channel. In today's video we're going to be looking at applications of a differential equation in a particular question. Let's just get straight into it. So we're going to be using example 13, and this is the diagram provided. I've just screenshotted it because it was on the other page, and quite frankly I like how it's set up now. Suppose the tank containing liquid has a vent at the top and an outlet at the bottom. So this following diagram here, so there's the vent and there's the outlet at the bottom, and through which the liquid drains. Okay, so Torik's law states that if the t seconds after opening the outlet, the depth of the liquid and the surface area is then this following thing. So this is a differential equation where this height is the height at the liquid at any point in pretty much the can. So for example, it doesn't have to be here. It could have drawn it up here, and that could have been h. So h is a variable. It's a function of time pretty much. So what we have is pretty much, alright, there's liquid in a cylinder and it's coming out and it's slowly decreasing over time. And we're given the dimensions of our cylinder pretty much. Okay. So we have dh dt, where we have negative k, where k is a constant, I believe, h is our variable, and a, I believe, is the surface area of the liquid. So that would be this surface area here, which would be the area of a circle in this case here. The constant k depends on factors such as viscosity of the liquid and the cross-sectional area of the outlet. Applying, I do not know how to pronounce this person's name, law to a cylindrical can which is initially full with a height of 1.6 meters and a radius length of 0.4 meters. Use K as this. Construct the appropriate differential equation and solve it, and find how many seconds it will take for the tank to empty. Okay, so this problem isn't that hard because one, we've been given this and we've been given pretty much the radius of this, which we can then use to find A, and then it's just the separation of variables. So we write our equation dH dt equals negative k square root of h on A. Now A is the surface area of our liquid, which is the area of this circle here. Now we've already been given the radius, so the area of a circle is pi r squared, and we've been told the radius is 0.4 meters. So your area is going to be pi 0.4 all squared. Okay, so 0.4 is the same as 2 over 5, so squaring that is going to be 4 over 25. So in other words, we're going to have the area is 4 pi on 25. So I'm leaving it as exact numbers because we're probably going to I don't want to really have decimals and stuff when solving the differential equation. Alright, so k in this case is 0.025. So that is the same as, so 0.25 is the same as 1 over 4. So adding that extra 0 just means it's 1 over 40 pretty much. So 1 over 40. Right, so let's sub our information into our differential equation. Now notice our differential equation is dH on t, but we only have h here. But we need to solve for t, so that means we're going to have to flip our equation eventually, pretty much, to separate our variables. Because remember, if we were to integrate right now, we'd be integrating with respect to t. But we don't have t here, so we need to flip it eventually. Okay, so 1 over 40, let's just plug the stuff in at the moment. So dH dt is going to be negative 1 on 40 times by the 1 over the area. So the area was this. So since it's 1 over, just flip that. So it'll be 25 on 4 pi. So 25 on 4 pi square root of h. Okay. So let's just try and work out what this would be. So for starters, if we go 40 times 4 is going to be 160. So therefore it's 25 over 160. I don't know how to simplify that. I'm just going to plug it in the calculator. We should get 5 on 32. So in other words, what we're going to have here is dH dt is, now don't forget the negative 5 on 32 pi, and then square root of h. Okay. Now, we've also been given something else in this problem. We got told the tank is initially full. So, when t equals 0, the height is all the way up here, which what we've been given, that h is 1.6 meters. Because if it's initially full, that means this h is going to be this one up here, very full. So this h here is a variable because it's going to change over time, but this is the maximum height it can be. And since we said it's initially full, it has to be that height. So we have when t equals 0, h is 1.6 meters. So we'll use that in a second, okay? Now, what we got to do is pretty much try and solve this differential equation. So at the moment, we can't integrate because we have h over here. So what we're going to do is flip our differential. So we'll have dt on dh. And that means we're going to flip this entire thing. So we'll have negative 32 pi on 5. And then we're going to have h to the negative a half. So up here, another way to rewrite this would just be h to the positive a half. But because I'm flipping it over a fraction, I'm going to give it a negative exponent. So this is another way you can write it, and I've just flipped it, so I've given it a negative exponent. Okay, so now if we were to integrate both sides, we can do it with respect to h, alright? So this side here, we're just going to get t. Here, we can take the constant out the front, so we have negative 32 pi on 5, and just integrating h to the negative half with respect to h, okay? So what we're going to do is add 1 to the power and divide by the new power. So we have negative 32 pi on 5, h, and we'll have a half. Divided by a half is the same as timesing it by 2, so I'm just going to put a 2 here, and a little dot, so we'll times, and then plus a constant pretty much, okay? So, 32 times by 2 is going to be 64, so we have t equals negative 64 pi on 5 square root of h plus c. And that's about it for now, okay? Now we've got to use our initial conditions to find out what this c is, okay? So at the moment, we're just trying to find an equation for t and h before we even answer our question, because we need to, what was the actual question again? I forgot what it was. How many seconds it will take to empty the tank. Okay, that's easy. Right, so put this in. So when t equals 0, h is 1.6, okay? So 0 equals negative 64 pi on 5 square root of 1.6, okay, plus c. All we're going to do is make c the subject, so move this fella over here. So we're going to have c is equal to 64 pi on 5 square root of 1.6. Now I'm actually just going to leave it like that. There's no really other way to simplify it unless you want a really weird decimal. So that means t is negative 64 pi on 5 square root of h plus 64 pi on 5 square root of 1.6. Okay, so this is our entire equation here. So if you want to work out how many seconds it takes to empty the tank, we need to think about this. When it's empty, that means this h here is going to be 0. So all we got to do is plug in h equals 0. So if you plug in h equals 0, so when tank is empty, h equals 0. So when t equals negative 64 pi on 5 square root of 0 plus 64 pi on 5 square root of 1.6. Alright, so that term's gone. So t is going to be whatever this number is. Now you'd plug that into your calculator now to get your decimal. Square root on 5 square root of 1.16. So you get 50.86. So if we're rounding that, was like 51. And is it in seconds? Yep, it's in seconds. So roughly it'll take 51 seconds to empty this particular tank. But anyway, that's about it for this video. I hope you enjoyed this differential equations application of it. I'll probably do another one very shortly. But yeah, if you had any questions at all, leave some in the comments and I'll try my best to answer them.